Okay, can everyone see the PowerPoint?
Yeah.
Okay, thank you for the information. Perfect. So today I want to start chapter 4, and chapter 4 is about timers and how we are going to use timers in our programs. But before moving towards timers in PLC, I want to start with the older version of timer, which is the mechanical timing relay, and see how we were able to implement any time action in our process previously, and how we are going to replace it with with our PLC instructions. So a lot of time when we are implementing an application, what we have is an instantaneous action. For example, you have a switch where you want to turn on, like activate a couple of switches, and with a particular configuration, such as having them ANDed or ORed together, you want to turn on a motor or an actuator right away. So a lot of time the actions are instantaneous, but it's not the application. This is not the application all the time. A lot of time what we require is some sort of delay in the process. So you want to turn on the switch, but you want the motor to start working after 10 seconds. Or you want to turn it off and you want the motor to turn off like after 1 hour. So a lot of time there is a time sequence involved as well. So we require to have some sort of fixed or variable delay in the process, and that will be possible with suspending the movement of the contact whenever the coil is energized or de-energized, or in both scenarios. So what we want to do basically is making sure that there is a time delay, and this time delay will be created by a pneumatic action which controls the release of air. So as soon as the coil is energized, there would be some air release, and this air release needs to reach a particular amount. We need to have particular amounts of air in order to activate the contact. So it will create some sort of delay in the application. And then these pneumatic timing relays, they do have different range of delay. So the delay can be anywhere between 50 millisecond up to 180 seconds. And obviously, because it's a mechanical relay, it always requires to have, so it will have some sort of drift over time. So it requires some sort of maintenance constantly. And it comes with that contact is very similar to a standard contact, and it comes with different range for voltage and current. The current is typically in the range of 10 amp. Okay, so what I want to talk about here is how this delay will work on different contact. I'm going to get back to this slide, but I need to add a couple of new pages. So give me a second, because I don't have the board, so I'm going to add a couple of a slide here. I think that should be enough. So let's take a look at what happens when we have a relay which is a timed relay and not a standard one. So let's assume that this is the signal we have from the coil. So that means at the beginning here, the coil is de-energized. Then here, the coil is energized. And again, the coil is de-energized. So this is the signal we have from the coil.
I think you might be on a different desktop for sharing it. We can't see it.
You cannot see that? Okay, so let me share it again. Mm. Can you see this now?
Yep.
Okay, perfect. Thank you. So here is the coil, and we know that if it's in a standard relay, then what we have for the contact of the relay is going to be something in this form, that when the coil is energized, de-energized, the contact of a normally open contact is going to be open. And when the coil is energized, the contact will be closed. And again, when the coil is de-energized, the contact is going to be open again. So what happened with a normally open contact of a standard relay is that it's going to instantaneously follow the actions that we provide. So there are two different actions. So there are two different actions here that you can see. There are two different actions. One of them is this action, where we have a transition from de-energized to energized, or we can say a transition from 0 to 1. And the other action is here, where we are going from an energized coil to a de-energized coil. So this is the other one. We are going from 1 to 0. Now, when we talk about timing relay, when we want to have a delay, then the delay can happen with any of these actions. So the contact that you can see here, we call it as instantaneous contact. So this is instantaneous contact, which can follow the actions right away. So as soon as the coil is energized, it's going to close. As soon as the coil is de-energized, it's going to open. So this is an instantaneous contact, which comes with a time delayed contact as well. Now, here I want
We
to show.
still can't see.
Yeah, I think it doesn't show it again.
Oh, what's going on? Okay, are we back? Can you see that now?
Yeah, write something though to see if we can see if we can see the writing.
Oh, okay. Yeah, so I think you should have it. If you can see the page, then probably it's good. Okay, so the one that you can see here is the instantaneous one. And then now we want to look at how we can have the time delay action. The time delay action happens either in as an on delay or off delay. What does it mean? So if it's an on delay, it means that the delay is happening in following this action. So this is an on delay. And off delay means that the delay is happening in following this action. So this is going to be an off delay. So let's see what happens in on delay and off delay. If I have an on delay, for example, 5-second on delay, then this normally open contact will follow this action with a particular amount of delay. So it's going to happen here. So after, for example, this amount of time, which is whatever we set for it, so this is our delay, then it's going to turn on and it's going to follow the other action right away. So it only has delay in on delay scenario. So when it goes from 0 to 1, it has delay, but it followed the other action right away. So it has an instantaneous action for going off. So this is what we call as an on delay normally open contact. Now, another contact that you might see is normally closed. So if you have a normally closed contact, then its instantaneous contact would be something in this form. So it's going to be open at the beginning. It's going to be closed at the beginning when it's de-energized, and it's open right away here, and then again close. So this is a normally closed contact. Now, what happens if there is an on delay and a normally closed? So if you have a normally closed, on delay happens here, right? So what happened here is that, and it is closed at the beginning. At this point, we have the action of opening, but it's not going to do it right away. So it's going to wait for 5 seconds or whatever is the delay time. So it's going to wait for this delay, and then it's going to close. It's going to open. The other action, again, it's because it's an on delay, the other action is going to happen instantaneously. So this is an on delay scenario in a normally closed contact. So what we have here is the first one here is a normally open contact, which has delay on whenever the coil is energized. And the second one is a normally open and normally closed contact. And again, the delay is happening when the coil is energized. So on delay means that coil is being energized. When the coil is energized, then we are going to experience the delay. Now, what is the name of these two contacts? You understand what does it mean to have an on delay normally open or normally closed, but when you see those contacts in mechanical relay, it has a different name. This one, the normally open on delay, is called time close normally open, and this one is called timed open normally close. And it makes sense. So it requires a time. The first one, the normally open one, requires time to be closed. So it's timed closed, normally open. And the other one is required time to be open. So it's timed open, normally closed. So if you have any of these two on your timed relay, then that is referencing to the on delay scenario. So this is the contact type, and then the combination shows that this is an on delay. Any question here on delay, normally open or normally closed? So you will see the picture here. So here you can see the coil, and then both of them are showing an on delay, which means the delay is happening when we are having an energized coil. So this 5-second delay is happening here in closing the switch. So it's going to be timed close, normally open, timed close, and this one is normally closed, which require times to be open. The other scenario that we have is going to be off delay. So off delay is going to work in the opposite way. So here what happened is that I'm going to draw it because it's going to be easier. So let's assume that this is the coil. And we do have, for example, a normally open and normally closed contact. So normally open instantaneous contact followed right away, and normally closed also followed right away, but in the opposite direction. So it's going to be like here, this one is open, and this normally closed will be closed, and vice versa. Here it's going to be closed, and this one would be open. Now I want to show you what happened if we have off delay. With an off delay, the delay is going to happen here. So it means this action will be followed immediately. So if I have a normally open with delay, then this action will follow the signal immediately, but the other action will require some time. So it takes some time, whatever is the time delay, in order to close, in order to be open. So this is going to be a normally open, which requires time to be open. So we call it as normally open, timed open. The other one, again, follows the first action immediately. So whenever the coil is energized, it's going to follow it immediately. But it takes time for the action, this action, when the coil is de-energized. So if it was an instantaneous contact, it would have followed the blue line. But here, it takes time. So for example, 5 seconds for the contact to be closed again. So this is a normally closed, which requires time to be closed. So we have a normally closed, timed closed. So these two are showing off delay scenario for us. So it's important to understand how the contacts will behave when we have a delay, and depends on if it's an on delay or off delay, if the contact is normally open or normally closed. So here you have the picture. Here it's showing the coil here, and then it's showing that this action requires a little bit more time, depends on the delay, and same thing here. So the first action is being followed immediately. The off delay, when the coil is being de-energized, requires sometimes to be followed. But if we have an instantaneous contact, then it will be basically our standard control relay contacts, and it will follow right away. Whenever it's energized, it's going to be open or closed, depends on the type of the contact, normally open or normally closed, and vice versa. Other than mechanical relay, we also have electronic timing relays, and electronic timing relays will do the same thing for us, but they are more accurate economically. It's better than pneumatic timing relay, and it's more repeatable. It comes in different range of voltages, and then regarding the timing setting, it has anywhere between 0.05 seconds up to 60 hours. And then its accuracy is anywhere between plus minus 5% of the set time. Now we also have another piece that is a multifunction timing relay. The benefit, this is going to be a standalone device. It's not part of a PLC, but it has a lot of timing function. So if you want to have like a RAM function in order to follow an action, you can set different functions for your device. And it also gives you the ability to change the delay time and change it from on delay to off delay. So a lot of flexibility regarding the timing action can be provided by this device. It's not it's an electronic device, but it's not a PLC. So it's a standalone device, and you can use it for applications where you require to have any type of time delay. Now, why we need any of these? Why we need any of these devices if we have the PLC? So a lot of time your application is very simple, and you don't want to use a PLC. I'm going to give you some example. For example, let's assume that there is a hallway, and in a hallway you are putting sensors, and these sensors are supposed to detect the presence of a person in the hallway and turn on the light. And then if there is nobody in the hallway, the light should be turned off. So typically when we have an application like this, we want to turn on the light right away as soon as we see someone. And then when there's nobody, we don't want to right away. So as long, for example, the person is leaving the hallway, as soon as it's away from the sensor, we don't want to turn it off because probably the person is still leaving. It might not be in front of the sensor, but he's still leaving the hallway. So typically, we would like to have some sort of delay action in the process, making sure that turning off the device is going to happen by a delay. So you don't want to have a PLC for such a simple scenario where it's just turning on and off a light. So instead, you can just have a simple timing relay, and this timing relay will basically postpone the action by a certain amount of time, depends on how long you want to wait until, assuming that the person is completely out of the hallway, so you want to turn off the light. So these type of relay, we still use them, these timing relay, we still use them for simple application where it's just a delay being involved in the turning on and turning off the process. But we can also implement the same thing in the PLC. So now I want to move towards the PLC timer instruction, and I want to show you how we can have the equivalent, an equivalent object, basically, or instruction in our program that will mimic the behavior of a timing relay. So we can have PLC timer, and we can use them for any time delay application in our process. And something that you have to notice that is the PLC timer instruction is an output instruction. So if you plug it in at the beginning of the ladder rung, then you're going to get an error. So it's an output instruction, you have to remember. And then you can easily change the settings of the timer and the type of timer, and it's more accurate and repeatable compared to the PLC. The only thing that you have to be careful when you have a timer inside your PLC is that the scan cycle that we talked about it earlier in the previous class, it's going to affect your timing process. So if you have a very long scan cycle, it's going to affect the accuracy of your timer, because the timer is assuming that there is a very short scan cycle and the value of the timer is going to be updated. So you have to just make sure that in very long application, you are using a physical timer. So we're going to talk about it later, that in each PLC, there is an actual physical timer that you have access to. So you can use that physical timer, and that timer independently calculate the delay. But the instruction type timer, which are basically just a computer program to accumulate time segment, they depend on the scan cycle. So you just have to be aware that if your application has a long scan cycle, it's better to use a physical timer instead of an instruction. But to be honest, for our application and a lot of different application, the instructions are good enough. It's just for very complicated application that you want to focus on the physical timer. Now, in Allen Bradley, we have 3 different type of timer, which is going to be the same for all different type of PLC that you're working with. Almost the same, not exactly. So it doesn't matter if you are focusing on a PLC 5, SLC 500, or even a logic system. They are pretty the same. And if you understand it for one of them, you can easily understand it for the other ones. So there are 3 different type of timer in all of them, which are called TON, TOF, and RTO. TON stands for timer on delay. So it's basically showing you that if you require to have an on delay action, then you have to use a TON, which is a timer on delay. For off delay, you're going to go with TOF. So whenever you want to postpone turning off something, you probably have to think about an off delay timer. And then we also have RTO, which is a retentive timer on delay. So it's basically exactly similar to a TON. So RTO and TON are pretty much the same. And there's only one difference, that it's using the retentive memory space. So we are going to talk about what happens if you use a retentive memory for timer, which happens with RTO, and you're going to see the differences. But it's going to, in terms of what happens with every beat of the timer, it's going to be exactly similar to a TON. So what we have as an instruction is going to be something in this form. So it's going to be a block, and in this block you have to set the parameters for your timer. Again, remember that the timer block is going to be an output instruction, so you're not allowed to use it as an input instruction. And then you have to set the parameter. There are three to four parameters, depends on the PLC that you are using. Here for SLC 500 and PLC 5, we have 4 parameters. The first one that you can see it here is the timer address or the timer number. So if you remember, I'm going to show it here. It's going to be in the next slide. If you remember, on the left-hand side of like PLC, I showed you that you can see all those designated files. One of those designated file is the timer file, which is a file number 4. So if you click on T4, you have all the informations related to your timers. Now, how do we save those information there? So what happened is that basically in the memory that is assigned to timer or T4 file, you have structures, and then each structure for timer will save the information of one of the timer. So the very first timer that you want to save, you can save it in T4 colon 0. And T4 colon 0 means that I'm using file T4 and I'm using the very first structure number 0. So the first one is going to be T4 colon 0. The next one is going to be T4 colon 1, T4 colon 2, and so on. So T4 colon 1, for example, is saving the information of timer number 1. So your timer has a number, and the address of this timer is basically what you need to plug in front of the timer. So if you're using T4 colon 2, then it's referring to this timer, and all the data will be saved here for this timer. Why do we need to have an address or even a number for the timer? Because later when we want to refer to that timer and say, if the timer is done with the delay, I want to have this action in my application, I need to know what is the timer number so I can refer to that timer. So here you basically provide the address or the number for the timer. Now, a very common mistake is if you just plug 1, 2, 3, it's not going to understand it because you need to provide the exact address. And the address is T4, referring to a file T4, and then colon, which is structure you're trying to refer to. Now, that's the timer that the address of the timer that you have to plug in. The next one is the time base. The time base is basically telling you what is going to be the incremental change in the accumulator value when the timer instruction is active. So whenever your timer is active, it will start accumulating time segments. And whenever these time segments are accumulated properly, reaching to your preset value, it will say that, okay, timer is done and the delay has been created. So here we have a time base, and time base is just telling us what is each time segment's period. In Allen Bradley PLC 5 and SLC 500, this time segment, which is our time base, can be either 1 second, 10 millisecond, 1 second, 100 millisecond, or 1 millisecond. So there are, I think this is, sorry, this should be 0.01. So these are the options. Actually, you can see them here. These are the options. So either 1 second or 10 millisecond or 1 millisecond. Now, why they are different? So the reason is that based on what, based on the accuracy that you require for your delay, you're going to choose the proper ones. For example, if you need 10 seconds, you can go with just a time base of 1 second, because you can accumulate 10 1 second, and that would be equal to your required delay. Now, if you need to have, for example, 15 millisecond, then you have to use a time base equal to 1 millisecond. So by accumulating 15 of those 1 millisecond, you can get to your delay, right? So it depends on what is the requirement for the delay. You have to choose the best time base for your application. A lot of time, you can use any of them, but all you have to do is setting your preset value according to your time base. So that's the time base. So you can choose between those three options. And then the next one is preset. Preset is basically telling you how many of those time segments you need in order to have your delay created. So for example, let's assume that I need to have 20-second delay. So if I need to have 20-second delay, then I can go with 20 for the preset, and then with a time base equal to 1. So it means that 20 of this time base will be equal to my preset, will be equal to my delay. Or I can go with 1 millisecond for the time base. And if I have 1 millisecond, then my preset should be equal to 20,000. So this would be the preset, and this would be the time base. So at the end of the day, the result of multiplying your preset by the time base that you're setting should be equal to the delay that you require for your application. And what will happen is that as soon as your timer is activated, then the accumulator start accumulating this time segment. So if your time segment is 1 millisecond, it will start accumulating 1 millisecond, and whenever the accumulator value reaches to the preset value, then your timer is done, and you know that your delay has been created. Okay, any question up to here regarding timers and its parameters and how the on delay, off delay? So I don't want to move forward before answering your question. Is everything clear? I assume either everyone is sleeping or everything is clear. Okay, thank you. So now that we know about the parameter, the last one was accumulator, and you don't need to set the accumulator value. The accumulator value automatically will start increasing, and it will be whenever it reaches to the preset value, you know that your timer has created the delay, and it's going to be done at that point. So you need to set the preset value, but the accumulator is a parameter that you can just look and monitor how much delay has been produced. So you don't need to change your accumulator value by hand. Now let's see how what is the difference between the logic system. It's a very small difference, but let's make sure that we know the difference. The main difference comes here, where we don't have the address anymore, because in logic system, everything is tag based, and in a tag based scenario, we are going to use a variable name, and the variable name is going to be used in our application. So in a tag based system, we're just going to require to have assign a name, a variable name to this timer. So we are going to say that, for example, this is the pump timer, or this is the motor timer. So we are just going to give it a name. And then in the tag window, you have to declare the type as timer. So over there, you're going to say that, for example, I have pump timer, and the type is going to be timer type. So as soon as you have the type declared to be timer, then everything is good. Another difference is that here we don't have a time base. What happened to the time base? Here, there is a time base, but it's not optional. So you don't see that as a parameter. The time base here is equal to 1 millisecond by default. So you have to plug everything based on millisecond. So for example, if you need a delay of 1 second, then your preset value should be 1000. So by accumulating 1000 segments of 1 millisecond, you have your delay created. Okay, so now I want to talk about the bit values that we have in a timer. Um, Okay, so here you can see this picture. It's an interesting picture that you can easily understand what happens in a TON timer. So the first timer that I'm going to focus on is a TON timer. And TON timer is an undelayed timer. So it means that if this is my input signal, or basically the first signal is what we have for the coil, it's going to have the delay only at this moment. So this action and this action will require delay to happen. The other two actions, they don't require any delay to be followed by. Now, in the PLC, when we are using the PLC timer, there are 3 beats that we have to understand about their condition and their status while the timer is working. Those beats are called the enable beat. You are looking at them here. The enable beat, the timing beat, and then the done beat. The enable beat is basically telling you if the timer is activated or not activated. So enable beat, in another word, is very similar to the instantaneous contact of a relay, where it is following the condition of the coil immediately. So if the coil is energized, it's going to be closed or opened right away with the action following that action. But here, the enable beat is basically telling you what's going on with the input. If the input is true, it's going to be true. If the input is false, it's going to be false. So it's going to instantaneously follow the input. So if I tell you to draw the enable beat is going to be exactly the copy of the input signal that is being received by the timer. The next one, so it's just the activation of the timer, and the timer will be activated by the input. So if the input is true, the enable is going to show you that it's activated. If that input is false, the enable is going to be 0, showing that the timer is not activated. The other two are showing the process of creation of the delay. So whenever you need to have a delayed action, then this delay will be produced by the timer, and TT beat, or we call it as TT beat, or timer timing beat. The TT beat will create that delay. So right away here, you have an action that requires a delay. So the TT beat will start creating that delay for you. So right away at this point, this beat is creating the delay. And if let's assume that the delay is 5 seconds. So for 5 seconds, this TT beat is active. And when we have 5 seconds, the delay has produced and TT bit goes to 0, showing that, okay, I'm done producing the delay, so it's not going to be true anymore. So if you want to think about this bit, this particular bit is going to be true while we are waiting to have the delay, being produced, or making sure that the delay is completely created. So as long as we are waiting in the waiting process, this bit is true. If we have waited enough, then it's going to be 0, which means that we are not waiting for any more delay at this point. So after 5 seconds, the timer has created this delay. So what happens now is that the done bit which is basically your timed contact, will follow the action. So this action was supposed to be followed here, but it's going to be followed by a delay. So after this delay being created, the action will be followed by the done bit of the timer. Now, what happens to the other action that we have here? So this action is an immediate action because it's a TON. TON is on delay, which means it's gonna create a delay when we have a 0 to 1. So at this point, sorry, I'm running out of battery. So at this point, here, we don't require any delay to be happen. So this signal will follow this action right away. So the red action requires delay. The green action, it doesn't require delay. Now, the interesting part is so I made a mistake in the timing. Let's assume that this is, for example, 10 seconds. So the red action, I have a red action again here. So this red action should wait for 10 seconds and then I can follow this action. But what happened here is that before 10 seconds, so only for 7 seconds the delay is produced. And then right away I receive a signal saying that you need to go back to 0. So this is an immediate action. I have to immediately go back to 0. So here, I don't get the chance to go to 1 because the delay was not completed and it wasn't that action. I was waiting for 7 seconds. I had to reach to 10 seconds in order to go to 1. But before reaching to 1, I received another command. I received another action saying that you need to go back to 0. So at this point, the production of delay is stopped, and this is not going to happen. This is not going to do anything. So here you can see that the signal stays at 0 because it wasn't able to go to 1 due to not having enough time for following the signal. Do you have any question here? This is a very important signal flow that you have to understand. Okay, so if you don't have any question, I'm gonna move to the TOF, which is a little bit more complicated. I'm hoping that everyone is following. I'm gonna give you 1 minute to take a look at it and make sure that you are following this, and I'm gonna move to the next one, next slide. Okay, so now I want to show you what happens with a TOF timer. So here we have a TOF timer. TOF timer requires delay when it's going from 1 to 0. So when the input is going from 1 to 0, it requires a delay. So the delay is, if this is the input signal, the delay is going to happen here and here. So the red actions requires delay, and then the green action that I'm going to show you here is going to happen right away. Now let's assume that the preset is 15 seconds. So each delayed action will happen after 15 seconds. So here we have the enable bit, which is again the exact copy of the input. So it's going to show you if the input is activated or if it's not activated. So it's going to be the exact copy of your input. The next one is, so this is EN bit or enable bit. The next one is TT bit or timer timing bit. And here, the timer timing bit will only be true when the delay is being produced. So it's only true when I have to start accumulating for delay. So the green action is going to be instantaneous. It's going to be a right away action. So there's no delay involved here. So TT bit is not going to be active here. But the red one here requires delay being produced. So when I have this one, at this point, the TT bit starts accumulating time segment in order to have a 15-second delay. So at this point, when it goes to 0, it means that the delay is equal to 15 seconds. So after 15 seconds, it goes to 0. So whenever it's 1, it means that we are waiting for that delay to be produced. Now, what happens for the done bit? The done bit here is going to follow the immediate action right away. So this is going to follow this immediate action right away. But when it reaches to the red action, it requires 15 seconds of wait. So it's going to stay there. It's going to stay on top. It's going to stay closed until 15 seconds is done. After 15 seconds that you can see here, it's going to go back to 0. Now, again, we have another action, which is green. So a green action will happen right away. So this is the green action, which happens right away. Now, for the next action, it should wait until delay is being produced. Now, what happened here, and that's interesting, is that at this point, the delay will start being produced. So at this point, the timer timing is creating the delay, but it only takes 5 seconds before the next action comes into the play. So what happened here is that it has created 5 seconds of delay, but we received another action, which is an immediate action. So whatever delay has been produced here will be ignored, and the signal will stay here on top. It's basically, in another word, this action wasn't able to be completed because we didn't have 15 seconds afterward to complete this action. So each delayed action has a particular amount of time, a particular preset time that it requires to be completed. If we don't get the chance for 15 seconds, then the action will be completely ignored because there wasn't enough time for this delayed action to be completed. Any question on the TOF timer? Okay. Now, something that is going to make it a little bit confusing, and I think if you just know how to do the done bit, you also can understand this part, is that if you're using the close contact of the done bit, then you have to reverse this signal completely. But I'm going to show it to you later when we have the program. Now here, this part is talking about RTO. So what happened previously was that when you had this action, you didn't get the chance to complete this action because before 15 seconds, you received the next activation set point. So, or immediate action. So you were not able to complete it. Or in the TON scenario, this action was a delayed action and it never get the chance to be completed for that 15 second. So because it wasn't completed, everything was reset back to 0. And if there is another delayed action coming here next time, another 15 second needs to be created again from scratch, from 0. But when we are using an RTO timer, what happens is that when, for example, let's look at here. You have this input signal, and then this action is going to be at the beginning is going to be delayed. So the timer timing bit starts accumulating time, but because we didn't get enough time to complete it, it goes back to zero. If it's an if it's a TON, right away it will make the accumulator value reset to zero. So if you have, for example, accumulated 10 seconds, the 10-second will be reset to zero. But if we are using retentive memory with RTO, it's not going to count furthermore. It's not going to accumulate any more time segment, but it's going to stop it there, and it's going to wait for the next round of activation. So, for example, here, let's assume that 4 seconds has been accumulated. When the timer goes back to zero, TT will stop creating the delay, but next time it's not going to start from scratch. It's going to start from here. So it's going to start from 5 seconds, and it's going to reach to, for example, 10 seconds, and it's going to create the delay is created. So now the done bit at this point will be true. So the only difference between RTO and TON is that when we have a TON and it's while it's creating the delay, the TT bit is active, it's going to accumulate. As soon as the timer is deactivated by receiving a false input, then everything is going to be reset back to zero. The next delay should start from zero again, should start from scratch. The accumulator will be reset to zero. But if it's an RTO, it's going to stop accumulating. So it's not going to create the delay anymore, but it has the memory of how much delay I have created before. So it's going to keep the accumulator value at whatever time, at whatever step it was, and then it's going to continue from there. Now, because of this memory that is attached to the RTO, if you need the accumulator value to be zero, you have to use an instruction. You require to have a reset instruction, and the reset instruction will reset it back to zero. Any question? Okay, the last part I want to talk about here is how we are going to save the data in the memory. So when I have a timer, as I mentioned earlier, we are going to save it in T4 file. So the first timer is going to be saved at T4 colon 0. The next one would be at T4 colon 1, and so on. Now, each structure it has the capability of saving the information of one timer. And if you remember, we talked about it in previous classes that each structure for timer is equal to 3 words. Now you're going to see why we're required to have 3 words in order to save the information of each timer. So those 3 words, at word number 1, we are going to save the preset value. So the preset that you plug into your timer instruction is going to save as a preset value in word 1. Word 2 will save the information related to the accumulator value. So each timer has a preset, and depends on how much delay has been produced, it has an accumulator value. So you require to have 1 word designated to the preset, 1 word dedicated to the accumulator value. And then at word 0, you need only 3 bits. So we don't really care about all these bits here, but the most significant bits that you can see here at word 0 is going to be the enable bit, the TT bit, and done bit. So done bit is bit 13, TT is bit 14, and enable is bit 15. So this is how we are going to save. Now, if I tell you that this is the timer, and I need the TT bit of this timer. So this is how you're going to address to this TT bit. So I want to show you how you can address to each one of these bits. So if I need to know about the TT bit, this is TT bit, right? So for example, this is T4. What happened? let's say this is T40, right? So if you need the TT bit of this timer, it's going to be T40. So up to here, I'm just addressing to the timer I'm trying to refer to. And then I need to mention the word number. So dot 0 and then slash 14. So a slash 14 is going to say that you have to focus on bit 14. Dot 0 is telling me which word I'm referring to. So if you need to have access to TT bit, this is what you have. If you want to have access to done bit, it's going to T4, it's going to be T40. Up to here is the whole structure of the timer, then word 0, and then bit 13. Now, similar to what I have told you before, whenever the word number is 0, you can just drop it. So by default, it's going to be 0. So if you need the done bit, an equivalent way of mentioning that is T40/13. Same thing here, T40/14. Another thing that is going to be actually interesting and it makes it easier is that instead of 13, if you forget about the number, you can actually use dn. So it's going to work the same way. So T4:0/en is going to work the same way as if you mention the exact bit number. So dn is going to be replaced by 13. TT is going to be replaced by 14, and EN will be replaced by 15. So if you forget which one is located at which bit number, you can just use the abbreviation here. So I'm going to continue from here in the next class. I think that's enough for today. Do you have any question? So if you don't have any question, I'm going to stop it here. And okay, so I have recorded the